Okay, it's time to take our quiz over what you've learned today. So question number 1, give 2 examples of harmonic motion. So we did the pendulum, and we also did a mass hanging from a spring, but then we also talked about plucking a guitar. We also talked about taking a marble and putting it into a bowl and then watching it roll back and forth. And then we also talked about how even atoms in a material vibrate back and forth with harmonic motion. Question number 2, use the following graph to determine the amplitude, the period, and the frequency. And I know that this graph is really hard to read, but you can remember that you can always blow up the picture so that you can take a better look at it. This thing has a maximum, and then it goes down to a minimum, and then it goes back up to a maximum again, and then time t is going sideways, and then the amplitude is going up and down. So if you look very closely at where this thing is having its maximum, that's turning out to be 3 centimeters. So we would say then that the distance from the equilibrium point up to the maximum there is going to be 3 centimeters. Remember, do not measure this total distance. So the answer is not going to be 6 centimeters, it's going to be 3 centimeters. All right, now what is the period? So the period is going to be the amount of time it's going to take to repeat itself. So if you look at the graph, and so let's say that let's start it right here, and then let's end it right over here. So if you go and you drop this down to here, this turns out to be something like 0.2 seconds. So 0.2 seconds corresponds to right there. And then if you go over to here, it corresponds to 1 second. So therefore, if you subtract the two numbers, so 1 minus 0.2, you get 0.8 seconds. So that would be the period. So that's the amount of time that it's going to take for this wave to repeat itself. Now, if you wanted to, you could have extrapolated this thing down to over to here, and you could have used as one of your numbers 0, but then you would have had to, on this one over here, you would have had to have gone down to there, and you would have had to have tried to figure out what that number is. But when you subtract the two, you would still end up with 0.8. So it's the same period no matter where you're at on it. Now, what would we do with the frequency? So now, in order to calculate the frequency, we're going to use this formula here that says that the period is 1 over the frequency, but another way of writing that would be that the frequency is 1 over the period. So all we've got to do is we're going to say that the frequency is going to be equal to 1 over 0.8. And now you can do that with your calculator and get a real number. And then once you've done that, put the word Hz on the end, because that's the official metric unit for frequency. All right, so that would be the answer to that question. Calculate the period of a pendulum that is 1.5 meters long, and it has a 30-gram mass attached to it. Okay, so what variables are you given in the problem? Now this one's kind of tricky, so you want to pay really close attention, because I might just spring something like this on the exam for you. So what variables are you given? You're given a pendulum is 1.5 meters long. So what is that? L. All right, we're given a 30-gram mass. So what letter goes with grams? Grams is a unit of mass. mass is abbreviated by the letter M. Okay, but that's the wrong unit. So we would need to take this and divide by 1,000. But we really don't need to do that, because what is the device? The device is a pendulum. So we're going to be using this formula, and notice that the formula doesn't depend on M. So that means that we don't even need to write this down if we don't want to. It's not part of the question. Okay, and then what do we need to know? So calculate the period. So we're going to find what the period is. Did any of you put down frequency? I hope not, because what we needed was what is the period of it. All right, so what equation connects the variables? Well, we're going to use this equation, but it's not quite right, because what we need is the period. So what is the frequency? The frequency is 1 over the period. So let's write this down over here. 1 over the period would then be equal to 1 over 2 pi, the square root of the G divided by L. All right, so there's our working equation, because we want to know what the period is. Well, let's take that and flip it upside down. Remember, whatever I do to one side of an equation, I need to do to the other side of the equation. So if I flip this, then I get the period. But if I flip this, what do I get? Then I have to flip this, so it would be 2 pi square root, and I need to flip this, so it would be L over G. So there is our working equation. I know that that's pretty difficult. So we started with our equation for a pendulum. We substituted in for the frequency, that it's 1 over the period. And then we took the whole thing and we flipped it so that the period went up to the top. But if I do that, then I've got to flip this and I've got to flip this. Now there's more than one way of doing this one. So I'm just doing it this way, and then you can do it any way that you want, but just be very, very careful with the stuff. So we're going to now plug in our numbers, and we're going to say that this is going to be 2 times 3.14, okay, and then this number is going to be multiplied by the square root of L, okay, so my L was 1.5, and then divided by G, and G was 9.8. So sorry if you can't read that. So 2 times 3.14 times the square root of 1.5 divided by 9.8. So I'm not going to do it for you, but where would you start? Well, you could start here, 2 times 3.14. So again, that's going to be 6.28. And now we got to do the square root of, okay, now you can take 1.5 divided by 9.8 on your calculator, then take the square root of it, and then take that number and multiply it by 6.28. And that would be your answer. And then what unit? Okay, period is a unit of time, so your answer would be in seconds. Question number 4. If a spring is pulled back 3 times as far, by what factor is its energy changed? Okay, now we're going to use this equation. The energy is 1/2 the spring constant. How far back do you pull it? Squared. Now it's the same spring, so you pull it back this far, and then you pull it back this far. It's the same spring. So we don't care about this. And for that matter, we don't even care about the 1/2. But we are changing the R. So if it's 3 times further back, the answer is 3 times the energy. No. 3 squared is 9. So it would have 9 times the amount of energy. Number 5, give an example of damped harmonic motion. There's all motion is basically damped. So we did the one where you took a pendulum and you pull it out and then you let it go back and forth and eventually it comes to a stop. You could do the same thing with the spring. So if you take the spring and you pull it down and you let it go, it's going to oscillate up and down, but eventually it comes to a stop. Another one that you could do is if you've got a ruler. So if this is the edge of a table, take a ruler and put it off the edge like that, and then take your finger, push it down, and then let it go, and it's going to oscillate like this, but eventually it comes to a stop. Damped harmonic motion. Number 6, explain what causes resonance and the effect it has on the motion of an oscillator. So whenever the frequency that you are pushing a system matches the natural frequency that it wants to vibrate at, then it goes into resonance. So every object, when you pull on it or push on it and then let it go, it's going to want to vibrate at a certain frequency. Even the table. If you take your hand and you slap the table, you notice that the table vibrates at a certain frequency. That's the natural frequency of that table. So if you're pushing on that oscillator at the same frequency that it naturally wants to vibrate at, it goes into resonance. And so what changes during resonance? The amplitude. So the amplitude of the oscillator gets bigger and bigger and bigger until finally it will just destroy itself. And so that's what resonance is. All right, so that completes this lesson. And so in our next lesson, we're going to start to talk about what happens when things are moving through space as well as time. So I'll see you then.